Welcome, guys, to our presentation about computer vision. We will start talking a little bit about ourselves. So, Daniel, go ahead.
Yes, that will be me. I'm a backend developer, currently working on computer vision with Python and also doing Java API development. I'm a software engineer at Capgemini for Blue Harvest, and I've been working at Capgemini since 2017. If I'm not at work, you can find me in the gym or coding my own game.
And that in the picture is me. I'm Rodrigo Hammerly. I'm full stack developer working on computer vision lately in Python, Java, and sometimes TypeScript. I'm not related to computer vision. I'm a software engineer at Blue Harvest, that is a unit for Capgemini, and has been working for Capgemini since 2018. And solving complex problems on my family are my biggest passions in life. So, what are we doing currently? We are working in improving document processes in Dutch, one of the biggest Dutch banks. We are working with quality checks for these documents before they get processed. We are also improving these documents before they got extracted. Also, we are working in payslip data extraction, signature data extraction, and at the moment, other POCs related to computer vision. So let's deep dive a little bit into our journey roadmap for the theoretical presentation part of, So we are going to start talking a little bit about what is computer vision, then also talk about what we can achieve with it, how does it work in general terms, what are the current approaches to computer vision. We are going to have a look into morphological operations. That is one of the ways computer vision works. And also a little talk about what machine learning can provide to computer vision. And we are going specifically to talk to a YOLO algorithm that we are going to use in our live code session. And after this, we are going for the Q&A session before moving to the live coding part. So what are the learning goals from this session? We want that you, at the end of this presentation, will understand the challenges that at the moment we face with computer vision, some methods for image preprocessing. You also will understand the basics of object detection, and you will know the pros and cons of both methods and when they are usually being used. So we can start telling what's computer vision. Computer vision is a field of study focused on the problem helping computers to see and understand digital images and videos. It could be broadly be called a subfield of artificial intelligence and machine learning, which may involve the use of specialized methods and make use in general of learning algorithms. Computer vision spans all the tasks that we have normally with human-related vision, including seeing, sensing the visual stimulus, understanding what is being seen, and extracting complex information into form that can be used later for processing. We can already say that computer vision is a broad term, and there are differences between recognizing objects, images, and doing image processing. So what can be achieved with computer vision? Well, a lot of things nowadays are really using computer vision already. But for example, it enables self-driving cars to make sense out of the surroundings. Self-driving cars have cameras with different angles, and they process this information in real time. They read traffic signs, detect other cars. Computer vision also plays an important role in facial recognition. As we see, we have all these filters in our in our chats. We have our cell phones able to recognize our face to unlock. Also, computer vision it's very important in augmented reality. Anyone that have played Pokemon Go, a lot of games that actually enhance what we see in the current world, adding extra features, but these features need to understand the surroundings and how things integrate together. Also, it's less fun, but very important. Computer vision allows us to understand scanned documents and written information in different type of scenarios. And that's one of the things we do the most in our current assignment, trying to make sense of documents. So, yeah, I will let Daniel continue from here.
Yes. All right, so what I want to do is I want to start by looking at how human vision works first. So if we start with a high-level description, then the first thing that happens in human vision is that light reaches your eyes. Then this stimulus goes to the visual cortex in the brain. And then finally, our brains make sense of what we see. And in this case, in the picture, we see a tree. So if in contrast, we look at the way that a computer visualizes things, we see that the process is quite different. So first of all, a computer does not have eyes, nor does it have a brain. It does have a memory, but unfortunately, computer memory and human memory, they are not very alike. So any type of imagery that we want computer to see will have to be opened or loaded rather than to be observed. Then the image that is opened or loaded is generally represented by a grid of pixels, which are stored into memory. And that looks a little bit something like this. So we may have, in this case, a very small 3x3 image, with every pixel index in that array has a red, green, and a blue value. So if we consider an image that we have in high detail resolution, it means that this image is, for example, 1920 by 1080 pixels. If we were to calculate the total number of pixels in that image, yeah, it would add up to 1920 times 1080. And then you have for each pixel a red, green, and a blue value, which amounts to a total of 6.2 million pixels. Yeah, and that's quite a lot of information. So given these pixels, how can we be sure that once we've loaded this image, that we are actually looking at a tree here? So why is it hard for a computer to tell which area or which areas of this picture embody the tree? But on contrast, it's quite easy for us to say so. And the answer to that question is context. So yeah, if we look at context, context is very important when it comes to analyzing images. So our human brain is quite good at detecting patterns. Yeah, when we see something or when we experience something, the event is stored in our memory. And if we encounter a similar experience in the future, it's quite easy for us to determine our course of action based on prior experience. So that means that for a computer, it is actually quite challenging to recognize the same kind of patterns that we are able to. Yeah, in short, that makes it that the goal of computer vision is to make a computer capable of recognizing features in images or in videos, just the way that we humans do. And yeah, the problem that we see is that in practice, it's actually quite difficult to train a computer to see, to think, and also to interpret things like a human being. So yeah, there are some tools, some tricks that we can use to help the computer a little bit. And we will discuss two computer vision approaches during this talk. So in computer vision, there are two main approaches that can be found. On one hand, we have morphological operations. And on the other hand, we have a machine learning approach. So for both approaches, the library OpenCV is quite commonly used. OpenCV is a high-level abstraction framework. In simple terms, it just means that you can achieve quite a lot in very few lines of code. While all those operations are backed by quite complex mathematical systems, usually the effects and the use cases are quite easy to follow because, yeah, there's actually a visual result. If you apply a transformation to an image, you can show it, you see the output, you see what was changed in the image. So it's quite easy usually to follow along with what these operations do. How they work, however, can be a little bit more complicated. I don't have a background in complex math, and I think that should be a testimony to the fact that I think that anyone with a computer science background, given enough time, should be able to pick this up. So if we dive a little bit into how this works, we discussed already the representation of an image. It's usually a two-dimensional array, and it has red, green, and blue pixel values. But in general, when we deal with images in computer vision, we don't really care about specific colors. So rather than these specific colors, speed is something that is quite important. So when we deal with images, often what we do is we downscale the image to what is called a grayscale image. So essentially what this means is that we go from a red, green, and blue value to just a singular value, which is a grayscale, gray tone value. So this is a value, again, from 0 ranging to 255. And 0 being black, 255 being white. Yeah, like I mentioned, it's important because it actually makes it a lot faster. We have to process 3 times less pixels in an entire image. So an example can be seen here. This is a very pixelated image of Abraham Lincoln. If we look at how this is represented as a grayscale array, we see that each pixel has a corresponding value to how bright or how dark it is. And in the end, the representation just looks like a 2D array of numbers. So from grayscale, what I want to do is discuss the next operation that is used quite often, which is called binarization or thresholding. So what we do once we convert our image to grayscale is we can actually further decrease the complexity of this image through a process called binarization. So what binarization means is that in the end we will be left with only 2 values. Either it's completely black or it's going to be completely white. What we can do is then we can pick a number between 0 and 255 again. And this number is what we call the threshold. And we can tell our program that any value that falls below our threshold value, so if we go back here in this array, any number that is below, say, if we take the middle, 127, is going to be black. And any value above 127 is going to be white. So I have an example here on the right. We see that, let's assume that the one on the left is our original image. It's just a gradient going from black to white from left to right. So if we were to take a cutoff value or a threshold value of 127, so in the middle, we see that in the first result, we get the left side is black, the right side is white. And this method is just the inverse effect. So actually you just say, okay, rather than lower means black, higher means white, you inverse the effect. So you get lower is white and higher is black. So why is this used? Well, we use it to increase the contrast between background and foreground. And in doing so, we can actually filter out, again, more irrelevant data to just get very concise, more standing out features in an image. So I have an example of where it may not work so nicely. So we see here that if we have the original image, It's a Sudoku picture, but it's in grayscale. But we see that there's quite some shadow that causes different lighting in different areas. So in this case, if we take a cutoff value of 127, what we actually see here is that the result is not so nice as the one on top, for example. There's a solution to this. It's called adaptive thresholding. I think for the scope of this talk, we're not going to deep dive into how exactly it works, but just know that there's another way where instead of defining this threshold value yourself, there's also a way called adaptive thresholding, which can look at regional differences rather than just take the whole image and define one value and cut it off there. And that actually will generate a lot better results. Right, so for binarization, actually I have a small code example that I put together. So I created a simple GUI tool. Let me run this one. What I will do is I will move this here. So let's first open the original. We have a Dutch license plate here, as we can see. So this is our original image. And what I want to do is I want to show you what happens if we convert this to a grayscale and we change this cutoff value, so this threshold value. So if we load this image, we can see that, well, it starts, say, here, like somewhere in the middle, right? So we see that we go from this original image on the right to this black and white image in this window right here. So to experiment a little bit with what happens, if we go all the way here, well, we see that it becomes white. We see that it becomes black when it goes all the way here. And the reason being is because the values here are actually inverted. But you can see what this slider actually does when you move it around. Is you see that, yeah, you can even filter out, like here, the NL part of the license plate completely, like this. If you do too much, you see it starts getting too aggressive and it will eat away from the black letters also. So this is in a nutshell what binarization is. You just try to define a threshold and you say anything above this will become black or white, or vice versa. Right. So there we go. So the next topic that I want to discuss with you is called erosion and dilation. So in morphological approaches, something that is quite often used is called a kernel. And a kernel is something, usually it looks something like this. This, in this case, is a 3x3 cube, so to say. So if we look at the below kernel, if we look at the center of this cube, basically what these numbers tell us is how to transform something in relation to its neighboring pixels. So if we have this center value right here, we're basically saying that all of these values are 1, so there's sort of an even distribution outwards. So what we do in this case is that from the center of this cube, we will apply the transformation to every neighboring pixel with a factor of 1, for example. So there are two main methods here. So we have dilation and we have erosion. So what does this mean? So if we look at the character J that we have on the original image on the left side here, if we apply dilation to it, sorry, it should be the opposite, like this. If we apply dilation to it, we see that actually the pixels, the white pixels that make up the J in this case, they're dilated, so they sort of expand outwards. Whereas the opposite effect, erosion, we actually sort of chip away parts of these white pixels, and we make the pixel regions move inwards, actually. So to also give a similar example, I also have a a code example of this, again with the Dutch license plate. So what we have seen is the original image. Let me load it like here. So if we load in, this is just like the binarized version, right? This is kind of where we left off in the previous one. So in this case, the cutoff value was exactly in the middle. So we see quite a clean image here. So what actually happens is if, for example, we apply erosion or dilation, that actually it has an effect on the thickness or the way that the characters stand out with regard to their background. So in this case, we see erosion, we see the letters appear thicker, and we see dilation, and we see the letters become thinner. So yeah, what's interesting, maybe if you have a keen eye, you spotted it, but what's actually interesting here is that I talked about erosion, which of course takes away a part of the pixel regions, and dilation makes it thicker. Well, what we see here is actually the opposite. And the reason being is that because these operations, they work only on the white pixels in the image. So they will not work on the black, but only on the white. So if we look then at this example, erosion, it basically means it takes away some of the white pixels. And thus, in turn, it looks like the characters are bigger because there's more black. And the opposite, of course, is then true for dilation. If we expand the white area, we see that the characters become smaller. So in this case, again, like I mentioned earlier, the binarization is inverted here. All right. Then the last morphological transformation that we're going to discuss with you this session is blurring. So blurring an image is something that may be used to smooth out regions of pixels or even an entire image. Again, this is achieved through a kernel. So again, we have this cube here, for example. So we pick one pixel, and then we say how much blur to apply to the neighboring pixels. And in this case, because everything is one, it's an even distribution. So this is what we call an average blur. Right. So the thing is that if we want to achieve vision, yeah, it sounds kind of counterintuitive to make an image blurry. And yeah, so the question is this going to improve the quality? How is this going to improve the quality of a document? Well, the answer is that it really depends. In itself, a blurry image is definitely not improving the readability. Not really for humans, but yeah, similarly also it's not going to make it any better for computers. But there are, however, cases where blurring can actually help with pre-processing. And one such example is a noisy image. So noise just means that there is a distortion in the image quality, where usually you see like lots of grains and dots that cause interference in the image quality. So actually, it turns out that applying blur in these cases can actually quite effectively remove noise. But yeah, at the same time, it does come at a price also. So while it makes it a little bit more readable for a human, so if we take the picture here on the right, we see that the original image, it's maybe a little bit difficult to tell here, but I also have a code example for this where it's well a lot more clearly visible. So here you see that there are some dots, a little bit of noise on the edges of these shapes and characters. And if you apply blur actually to the human eye, it will look more smooth. And also this, yeah, I think is an effect that you can also see in some games, for example, where they use anti-aliasing. So this really, it's just a way of smoothing out certain details to make it look less jaggy. Right, so the price that I was talking about, actually it does make it more readable for a human eye, But for computer, we have a little bit of a problem, because if we smooth something out, it means that the contrast between the fore and background is also smoothed out. So the edges are a little bit less detectable. So all in all, it means that blurring is a tool that we should use sparsely. But yeah, we really need to also consider when it does or does not improve readability. And by proving this, I would like to again show like an example to show a use case where actually this is quite useful. So I mentioned that blurring is actually quite good at removing noise from an image. So if we look at an example here, let's look at the original one. So we have here, you can tell if I zoom in especially, yeah, this is very grainy, noisy. This is really a distorted kind of image. So if we select this one, this is the grayscale version of that image. So yeah, here we start seeing the problem with noise. If we binarize this and we just put the cutoff value in the middle, this is what it looks like. And we see that the noise, some of it is filtered out, but a lot of it actually persists even through binarization, because yeah, there's just a huge variance also in this pixel distribution. There's a lot of black and white interference. So if we want to achieve better results than this, I think what we should do is first take a step back. So we go back to this grayscale image. And then what we do next is we actually blur this grayscale image. And yeah, I guess already from this sub image, we can see that a lot of the noise has been sort of canceled out. It looks a lot smoother, but still, I think this on its own is still quite difficult for a computer to read. But let's have a look at what happens if you binarize it now. Well, then we see that the characters stand out a lot more actually, and we've effectively removed the noise from the image by binarizing it after applying some blur to it. Yes, so we've covered all the morphological transformations. So we've now arrived at the machine learning approach. And I think that the machine learning deep dive is a bit out of scope for this session, especially due to time constraints. But what we will do is we will lay out all the basic concepts of machine learning to you, and that should give you a pretty clear idea of how it works. So there are two methods that we will discuss. The first one that we're going to discuss is called classification. So with classification, what we mean is that we look at an image and we try to answer the question, what am I looking at? And a response might be, well, you're looking at a cat, or you're not looking at a cat. So the answer is quite binary. It's either a yes or a no. Is it there? Yes. Or is it there? No. While it's useful if we want to determine what we're looking at, usually what we also want to do is we want to know where something is in an image. So we also want an answer to the question, where is it in the image? So for that, we have localization. So basically localization, what it does, is if we look at the example here, on the left side, we have classification. It just says, okay, this is a cat. But if we combine them, so we have classification and localization, it's able to tell if there is a cat, yes or no. And it can also give me sort of approximation where it is in an image. But the limitation here is that actually it only works for a single object. So we have another method, the second method that I want to discuss today. And this one is called object detection. So for object detection, we used different classification modules, and they each look for different classes of objects in images. So it means that it is able to detect more than one object in a single image. So we are not so much concerned with the question, is this object present? But it's more of an agnostic use case where we want to identify a list of objects that are present in an image. In the next few slides, actually, you will see some examples also that will make this a little bit more clear to you. So the last one that we have is instance segmentation. If we look at the example image in here, we see that object detection is able to detect cats, dogs, and ducks. And usually how this works is that people have trained models to recognize these things, but we see that it's able to pick up different kinds of objects in a single instance of an image. Instance segmentation, what we try to achieve here is we try to find the enclosed shape, what we call the convex hull of an object. So we really try to isolate or approximate the full coordinates, like that embody this object. Right. So let's look back on what we know so far, and let's compare some things. So the two categories that we are going to compare with each other is, on one hand, we have pre-processing. So those are all the techniques that I explained at the start. Then we have object detection. And object detection, on the other hand, is a totally different use case, as we will see in this comparison. So it turns out that pre-processing is not really so good for recognizing complex features. What it is quite good at, however, is optimization for achieving computer vision. So if we find the location of, say, a license plate on a car, well, there are some tricks that we can use to actually make the characters more readable, for example. On the other hand, object detection is quite good at recognizing complex features, also different kinds or multiple features inside images. But it may not always be sufficient for achieving computer vision on its own. So if we think back to, for example, the noisy license plate that we saw earlier, well, it's clear that simply locating an object is not always enough, for example, to make it readable by, say, an OCR engine. If you are able to isolate the license plate, but it's very noisy, the quality is rather bad, still you will have a hard time trying to read it. So I think we can summarize it by saying that they each have different use cases, but in the end, they complement each other. So often you will see that you will be using both rather than either one. Then, for the last part of the after the presentation, we will be doing a live coding workshop, and during this workshop, we will be using a framework that is called YOLO, and YOLO stands for You Only Look Once. It is an object detection algorithm, and it helps us to answer the questions what and where in an image. In short, this means that we feed an input image to YOLO. It will use something called a convolutional neural network to generate predictions of what objects are present in the picture. That will look a little bit something like this. So let's have a look at an example. In this picture, for example, we see that multiple objects are identified. Traffic lights, people, trucks, cars, and if you have a keen eye, then here you see even a handbag, so a very specific thing. It doesn't do so out of the blue, because recognizing these things, usually what you see is that people train machine learning models to recognize these things. And this part is a little bit something, maybe a little bit abstract, but what I do want to do is try to explain on a high level what YOLO does and how it works. So let's assume that we have the picture on the left as an input image. This is somewhat of a simplified schematic overview. So we can see that the image on the left is actually segmented into a grid. And if we send this picture to YOLO, it will do two things. And again, this is oversimplified, but just to visualize it a little bit. So the first thing it will do is it will look for the object's location, and it will try to rate each box with a confidence score. So in the end, we see that we get a dog, a bicycle, and a car that are highlighted in this image. But how we get there, how does that work? I think it's probably someone spent quite some time on a process called image labeling. So what image labeling is generally what you have is, let's say that you want to be able to recognize dogs in images. What you will see then is that someone has, for example, say 1,000 images that do have dogs in them. And on the other hand, they also have 1,000 images where there are no dogs in the picture. In the pictures where there is a dog, they will manually sort of label the location of that dog, and they put them in, just an oversimplified example again, but you have a positives folder and a negatives folder. So every picture that has a dog, you highlight it, you put it there. Every picture that doesn't have a dog, you put it in the negatives folder. And basically that is used as input for training a machine learning model. So in the end, it will actually, because of all the examples, will be better at recognizing when a dog is found in an image. And this process usually is repeated for each class. So, and by class, I mean different type of objects. So a bicycle, a car, a dog. Then, in the end, some filters are applied and some of the objects are localized. So if we look at the bottom, for example, you see that there's a class probability map. And what we see here is that some tiles in the grid are highlighted with a certain color to indicate where possibly it thinks that that one of these objects may be. And then in conjunction with the above example that's trying to locate the bounding boxes and the confidence, it comes up with a prediction where it says, for example, I don't know, this is, I'm 84% sure that this is a dog, or I'm 90% sure that this is a bicycle. Right, so like I mentioned, I don't want to go too much into detail because this really is something that could take up a whole talk on its own. But I'm just trying to lay out the fundamentals because we will be using YOLO to recognize license plate in cars. So what we will actually show is YOLO in action during the live coding session. Let me think. Yeah, I think that's for now. That's all I want to say about YOLO. Then finally, what I would like to do is offer some time for Q&A. So if you have any questions at this moment, feel free to put them in the chat. Rodrigo and I will do our best to answer them. So yeah, I'm looking forward to what you have to hear so far before we move on to the workshop.
Hello. Hey, Rodrigo, also here.
Hey.
So I have a few questions written down. Let's start with I'll just try to do them in a kind of order, but it's rather randomized here on post. So here we go. Does a higher resolution image help the compute visioning tool?
Sometimes. Actually,
Sometimes.
yeah, actually, there is a threshold. When the images have very low resolution, it's really hard to find information. But as they grow bigger, actually, they put a lot of stress on the system, and most of the systems are tailored to work with certain amount of resolution, so some in between. So what we usually cannot do is like increase resolution when we have lower resolution images. But if they are too big, we usually lower down in resolution to be able to process. Also, every pixel that we add to the image adds more stress to the system, and it doesn't directly correlate with better results. It is to a certain degree.
Cool. That's good. Okay, I got another one that just popped in. Any idea what happens when you sharpen a blurred image? Does it return to the previous state or does it smoothen out?
Yeah, this one is an interesting one. So you mentioned sharpen a blurred image. So what I discussed during the talk is that if you have a noisy image, you can apply blur to it and it will fix the noise that's in this image. So what's actually funny is that if you have a blurry image, sharpening is like a tool that you have, for example, also in like Photoshop, for example. But actually, sharpening, ironically, is not the opposite of blurring. So if you want to make an image that is very blurry, sharp, it sounds very strange, but you have to add noise to it. So it can be like something like Gaussian noise or something. But to make a blurry image sharper, you have to add noise. And again, like I mentioned during the blur part also, is that if you try to denoise an image by adding blur, it comes at a price. But also the opposite is true. So if you have a blurry image and you add noise, you can imagine what effect that has on the readability of an image. So if you take an image and you blur it, usually it's something that if you want to read characters from it, especially if you have like a small document, then you actually, it's kind of a hopeless situation because you cannot really fix it. You can make it more readable for human, but not really for the computer. So blur and noise are quite detrimental to the progress of, the performance of computer vision techniques.
Sharpening is also like enhancing the contours of an image. It's not related to the opposite, to blurriness.
Yeah.
And how do you then let the program decide when it has to do some sharpening or blurring?
I can explain maybe a little bit based on what we do currently. So what we try to do is we just try to detect if there is any blur. And the thing is that what I mentioned is that if you try to correct it, actually, even though you might think that you make it more readable because you are able to read it better as a human being, it's probably because you add noise, all these kinds of random dots everywhere, it's going to make it still quite hard for a computer to read it. So it's something that turns out to be quite difficult to fix. So what we actually do is we try to say at the upload stage, we try to say, hey, we see that this document is quite blurry. Maybe you want to reconsider uploading because otherwise we have to look at it manually.
Okay, interesting. That's cool. And another question, but this is more on the machine learning part. How much images are needed for a machine learning system to start recognizing it properly? So probably with 3 images is not enough, but I don't know.
It's usually a couple of hundreds. 1,000 should be your target. It makes it really hard for things like in real case scenarios when you're working with customers and you're training your machine learning model with data that is, for example, real life documents that are related to customer data. You cannot use that, and it makes it really hard. There are certain shortcuts because you have pre-trained models. Usually you don't train a model from scratch. You use a trained model and you retrain it on top of it, and that usually require less amount of samples, but at least should be 100 or 200, and you always need to keep some of these samples for actually validating your model. So usually should be like 20% of your samples shouldn't be used to train the model, but to test it.
Okay, interesting. And Daniel, there was also a question popping up for you. We missed a cat. Where did she go?
Yeah, I don't know where she went, but she decided I have a glass of water here, and she decided that that glass of water was hers. So.
Interesting. So immediately a follow-up question about that then. Do you have like a home project going on where you're trying to recognize your cat in certain positions?
No, I don't actually. No.
Okay, cool. Then I've one, but that's probably a tricky question. You all know CAPTCHA, right? Are we
Yes.
training CAPTCHA with the computer vision technology by clicking everything?
Well, Google has a big image database that you can use for training your own models. It's free, and you can search for almost every object that you can imagine, and there are already images that are tagged there. So I don't know where they get those from. So
Okay.
maybe it's from the CAPTCHAs.
Yeah, you never know, right?
No.
Okay, cool. So I see just another question popping in from Sherif Sahin. I believe I once opened CV for facial recognition, and for reliable results, the sweet spot number was 50 or so. Does it differ too much from facial recognition to document recognition?
Well, that depends on what type of document you are working on. For example, if you just want to, in a passport, recognize where the regions of interest are, let's say the machine-readable zone, or like where the name, or that type of thing, maybe 50, it's too little. It has a lot of variation. You will probably need more samples. If it's similar, say the other way around, for example, passport, 50 could be okay. So that depends. There are documents that are pretty much well structured, so you actually expect to find information in the same site area, and that is easier. But if you have a big variation between the different samples, then you will need like a bigger training sample.
So basically, the more the better.
The more the better, but yeah, that depends. If you are using something that is pretty much similar in every case, so there is no big variation, as I said, like passports, then a smaller like sample is okay. But if you have something that changes a lot, let's say it's not document, but like a flower or a chair or something that, well, there could be so many different models of it, then you will need a bigger sample size.
Great to hear.